Okay. So I think we have already 40 people. I think we can start as a day.
Yes, I will start presenting, right?
Okay, cool.
Okay. Hello, everyone. Our this week's speaker is Professor Andrzej Wereszczynski from Jagiellonian University, if I'm not wrong. And the main focus of his research is on topological defects and their interactions. But I will leave it to Andrzej to explain better what he's working on. And Andrzej, once again, thank you for accepting our invitation, and you can start whenever you want. Thank you.
Okay, thank you, Azadeh. It's also my pleasure to have this opportunity to talk to you. And yeah, let me start. I will. Okay, I'm sharing. Okay, do you see my slides?
Yes, that's
okay, perfect. So thanks again, Azadeh. It's really fantastic to speak to you. It's almost being in Brazil. And yes, that's true. I'm going to talk about dynamics of topological solitons and a way how we can understand these dynamics. Okay? And this a sort of summary of my ongoing work with in a collaboration with quite a few people, like Christoph Adam from Santiago de Compostela in Spain, and Nick Manton from Cambridge, UK, and then also Professor Wojtek Zakrzewski from Durham in UK, and my local collaborators in Krakow, Kasia Oleś and Tomasz Romańczukiewicz. Okay. And to be more specific, the contents of my talk is the following. I would like to show you a sort of a method which is like the standard method of understanding of interactions of topological solitons, and it's a collective coordinate method. So I will start telling you why this method is important and how we can construct a collective coordinate models which can explain the dynamics of solitons. Okay? And then I will introduce two notions. One is like frozen vibrational moduli space, which is a method of building collective coordinate models. And then I will show you that this method, which is very simply, allows to explain really complicated non-integrable phenomena, like kink-antikink collision in phi-to-4 model. But then I will concentrate rather on cases where this the simplest construction of collective coordinate theory is not sufficient, and then you have to create something which we call dynamical vibrational moduli space. And I will try to explain this concept and present situations, cases where it's necessary to consider this modification of the original way of constructing of collective coordinate models. Okay, so what is the collective coordinate method? Okay. It's the definition is really, simply, it's just a reduction of complexity of theory which possesses topological solitons. Because for a given model, for a given theory, where you can find topological solitons which are like very complicated, which are solutions of some non-linear partial differential equations, which also carry topological charge. So those theories are quite complicated in the sense that they are non-linear, and the interactions between solitons, between the topological solitons, is really involved. Okay, there are many ways solitons can interact, and therefore the dynamics exhibits really a variety of possible phenomena, and it's hard in many situations. It's very hard to understand. Okay, so what we would like to do is to have a method which can give a sort of analytical or semi-analytical insight in this very complex dynamics of topological solitons. And one way, the most popular, is to reduce infinitely many degrees of freedom, which are in the original field theory, because you have field, right, which always carries infinitely many degrees of freedom. And yeah, you want to reduce this infinite number of degrees of freedom to finite subset, okay? But this finite subset should somehow consists of only crucial degrees of freedom, okay? So in this construction, the original field theory is replaced by a classical mechanical system. Instead of Lagrangian, which is based on field phi, you have Lagrangian, which is based on a finite number of degrees of freedom, xi, right? All right, this is like very vague definition or idea, but why it's important? First of all, it's important because it can give exactly a semi-analytical insight into dynamics of topological solitons. It can explain in some situations what is a reason, what is a mechanism behind observed properties, okay? And I will show you an example. In higher dimensions, this method is also very important because dynamics of solitons, of topological solitons in higher dimensions is of course much more complicated than in a one-dimensional system. And then it's it's not easy to do numerics even, right? In one dimension, it's almost trivial, or it's not too complicated to scatter kinks on a line and then see what your field theory produces. But in higher dimensions, like in the situation where you have abelian Higgs vortices or monopoles or skyrmions, it's really complicated to do to find static solutions and then to really scatter them and like to try to understand the whole variety of possibilities is almost impossible. And this simplification gives you a chance to understand the dynamics, okay? And the last important field where this collective coordinate method is really essential is the semi-classical quantization of solitons, because solitons are very non-perturbative objects, and therefore it's not easy to quantize them, okay? It's not like quantization of vacuum and then doing perturbative expansion. Here, the object which you would like to quantize is completely non-perturbative. And a way to quantize such a soliton is to find out some important degrees of freedom, which are really like so the philosophy is exactly like in the reduction or in the collective model construction. You have to find out important degrees of freedom, and then you should quantize them. And it's always a finite subset of degrees of freedom you quantize. Okay, So this collective coordinate method is related to, is very related to semi-classical quantization of topological solitons. Okay, so we know what it means to construct a collective coordinate model. Okay, it's just a reduction, but how to construct it? The crucial idea is to find out a restricted set of configurations which is important for a given process, dynamical process you want to study. Okay, and then this set of configurations is it can be solutions. It can consist of static solutions of your model, for instance, but it's not necessary. It doesn't have contain only solutions. It can be some configurations which are not really static solutions, but typically they are parameterized by some parameters. So yeah, and it's an educated guess. You somehow have to capture the main, your restricted set has to capture the main properties of a solitonic process. Okay, so it's not there's no like canonical prescription how to construct this restricted set of configurations for any solitonic process in any field theory. But there are many cases where we do have a sort of canonical procedure, okay, and we know how to construct this set, although there are many open questions also. Okay, but once you have this restricted set of configurations, you insert them into your original Lagrangian, okay, and then you integrate it over the spatial coordinates. In this case, I will consider only 1 + 1 dimensional field theory. So I integrate over x coordinate, and then you include all dynamics into your parameters. Okay, you assume that all dynamics, all time dependence is hidden in time dependence of the parameters which parameterize your restricted set of configurations. Okay, so at the end you arrive at a model which has this kind of form. It has a kinetic term, okay, because the time dependence is only due to these x coordinates, which are coordinates on your moduli space. Okay, and so this kinetic term is multiplied by a sort of metric on the moduli space, and it's really like a metric. It transforms like a metric under the change of coordinates. Okay, and there is also a non-derivative part, a potential, an effective potential, which originates from the derivative term of your original Lagrangian and field theoretical potential. Okay, this metric is usually a smooth function without singularities. Okay, but sometimes it has singularities, and sometimes this singularities is not just an artifact of a badly assumed coordinates, but singularities can be related to physical phenomena. Okay, so it's important to realize this. Okay, so next step, how to find this restricted set of configurations, which is crucial in this approach, right? So as I told you, there is no one way which can be applied to any field theory and any process. But in some cases, we know how to deal with this problem, okay? So there is a canonical moduli space in the situation where you have a set of energetically equivalent solutions. Okay? If you have a system with a soliton, and then there are some static solitonic solutions which depend on an internal parameter, and all these static solutions have exactly the same energy, then we know how to construct the moduli space. Such a theory is called a Bps theory, and such a regime is it's a Bps regime where your solitons basically do not interact with each other. For instance, if you have two solitons of a given charge and they are separated, then they have exactly the same energy as in the case that they are on top of each other. So they are really, the distance between them is zero, right? So there are many very important physical models with this property. It's Abelian-Higgs model with critical coupling. It's Toft-Polyakov monopole. It's there are these two the most important, but there are also many others in some condensed matter physics or in nuclear physics. So it's quite large set of theories with this property. Right, and then you can build your canonical moduli space as using these static solutions which have exactly the same energy, because now the simplest dynamics, the lowest energy dynamics, happens just through a sequence of energetically equivalent solutions, right? So to go from one solution of the same of energy E to another solution of the same energy, you need basically zero energy excitation. You need arbitrary small velocity for your solution to pass through all static configurations with the same energy, right? And it's equivalent to the fact that your theory has a zero mode, which allows you to travel from one energetically equivalent solution to another one. Okay, so let's consider an example, and it's phi-to-4 theory on a line, okay? So it's one-dimensional field theory with time-dependent field, and it has a kinetic term, it has a gradient term, and it has a potential which is the simplest double vacuum potential, and we have vacuum at +1 and -1. And there are topological solitons in the theory, and they interpolate between one vacuum and the other. Okay, so there is a kink which goes from -1 to 1, and it's tang x, and there is also anti-kink with the opposite sign. And because the theory is Poincare invariant, okay, it has translational invariance, so you can put your soliton, your kink, at any position, which means that you can add a constant to the argument of tang. Okay, so changing A means that your function has 0 at x equals A, so it has different position, right? Different positions. And if you plot energy density, then you will see that this energy density is concentrated around the point A. So changing A means that your kink is located at different point, right? So, okay, so we do have a restricted set of configurations. All of them have exactly the same energy. So let's plug this set of configurations of solutions, in this case, into the original Lagrangian and integrate, and then we arrive at this effective theory, which is a collective coordinate model, a collective coordinate model. But if you compute these integrals, then you find that your metric is, of course, one-dimensional because you have only one modulus. And it's a constant number. The same with the potential. So you have a constant potential, which is immaterial in this case because it's constant. And then your dynamics is just your equation of motion for the modulus A is just that the second derivative of A is equal to 0, which means that this collective model captures only a kink which moves with a constant velocity, okay, which is a solution of equation A double dot equals 0. Okay, so this is an example of canonical moduli space, which is almost trivial. It describes only a kink which travels with a constant velocity. Okay, you can of course observe that your Lagrangian, effective Lagrangian, is non-relativistic Lagrangian, although you started with relativistic field theory. So this is a global feature of the collective coordinate method, that it always brings a relativistic model to a non-relativistic effective theory. This is the current status. It can happen that soon it will be different, but yeah. So let's move further and extend the set of restricted configurations. Okay, so we can go beyond the simplest assumption that we consider only energetically equivalent solutions. So we add some other solutions. Okay, so we extend this set, and this is the problematic step, because basically we do not know how to extend it. But of course, one educated guess is that you add some massive excitations. We started with 0 modes, which means 0, like zero energy excitations. So now we add some massive excitations, which means massive modes in a small linear perturbation theory. So you have your kink, you perturb it, you compute the Sturm-Liouville problem or Schrödinger equation, and then you obtain the modes which are hosted by this soliton. Okay, and then if you find something, you can include the amplitudes as an addition. Yeah, you can consider the amplitudes of these internal modes, massive modes, as another moduli on your moduli space. Okay, so now, of course, because now the energy of configurations included in the restricted set of configurations are not the same, because if you excite a mode, then you increase the energy of this configuration. This configuration usually, always, I think, the energy grows once the amplitude of the mode grows. Okay, so the energy is not now like a flat, but has some directions on your moduli space where the energy grows. Okay, and we can again use phi to 4 theory as an example and consider a kink at any position with a mode excited on this kink. And in fact, yes, in phi to 4 theory, a kink, the kink has a shape mode, has a normal mode, and there is only one normal mode for kink, and it has this form. Okay, so it's sinh x divided by cos x, and it has frequency omega squared equals 3, and it's of course below the mass threshold. But important fact is that for phi to 4 kink, there is only one internal mode. Okay, but it gives a natural extension of your original canonical moduli space. Okay, you include this massive excitation to your kink, and now you have a more general set of configurations. You plug them to your original theory and obtain the collective coordinate model. Now it's more complicated. It's two-dimensional moduli space. So the metric has two components because the non-diagonal part vanishes. The potential now, it's not trivial. It depends on the amplitude. It's related to the fact that what I said before, that increasing the amplitude of the mode usually increases the energy of the configurations. So yeah, if you solve it, the solution is just a kink which moves and vibrates. Okay, so this is the sort of dynamics you can capture or describe by this collective model. So you see that the dynamics, the collective model has to be always tailored to a dynamical problem you want to study in a given model. Okay, so if you would be interested from the very beginning with a single kink moving and vibrating, this is an effective theory which describes this dynamics very accurately. Okay, but of course it's boring, right? When you have one kink which vibrates, it doesn't mean anything else, any other kink, any anti-kink, so it's really boring. The most interesting case is a case where a soliton collides with another soliton. It can be another soliton, or it can be another anti-soliton, and then you can consider something really interesting. Okay, it's much more interesting, and there are two ways how to build this set of this restricted set of configurations, which will in the end give you the moduli space and a collective coordinate model, right? One method is what we call frozen vibrational moduli space, okay? Because in all cases, in almost all cases, when you build, when you consider, for instance, a kink-antikink collision, and you want to build a collective model, your building blocks typically are simply the one soliton states, okay? So we do have one soliton state here, for instance, right? We have a kink which vibrates, and the moduli space of the restricted set of configurations is this is exactly this configuration. So we can find something like that for anti-kink also. And then the frozen vibrational moduli space for kink-antikink collision is just a superposition of moduli spaces of three completely independent kink and anti-kink, for instance, in this case, right? So you see, this is kink in 5-4 theory, and this is its shape mode, okay? Its amplitude, and the kink and its shape mode are, everything is of course located at one point. It's x equals -a. And we have also anti-kink, and it's located at a, and it has its own shape mode. Here, it's only the symmetric superposition of these modes for simplicity. So this configuration here describes a frozen vibrational moduli space, which can hopefully capture a dynamics, a kink-antikink collision in 5-4 theory. Okay? But the name frozen comes from the fact that from the very beginning, we assume that modes, here there's only one mode, but modes are not deformed by the presence of the other soliton, okay? Because what we did, we just made the simplest, the most naive superposition of two one-particle states forming a two-particle state. Right? So, for instance, this mode, the shape mode has all the time the same form, although the soliton comes closer to the anti-soliton. Okay, so we just forget about the fact that one soliton can deform another soliton and then somehow can have an impact on the mode structure, because this is exactly what you would expect naturally. When the soliton and anti-soliton are on top of each other, when they meet, where A is equal to 0, this little a is equal to 0. So it means that soliton and anti-soliton are exactly at the same point. So these functions, they cancel, because you have tanh x minus tanh x, but also this cancels. Okay? So what you have just vacuum -1. And vacuum doesn't host any mode. Okay? So in a sense, you see that your configuration passes through a point which doesn't allow for any internal modes. So you would expect even that this frozen vibrational moduli space cannot work, but it works in many situations and it works very well. Okay, but having this in mind, you can expect that there should be some cases where this naive frozen superposition is not enough, and then you should worry about the fact that the modes they form, or even their number, can vary depending on the distance between one soliton and anti-soliton in this case, or between soliton and another soliton. Okay, and there are cases where this is important. Okay, so now we understand how to do what is the collective coordinate method, how to construct such an approximation, and let's see whether it works. And yes, it works, and you can explain a very long standing problem of kink-antikink collision in 5-4 theory, okay, using this simply construction. So if you consider a kink and anti-kink collision in 5-4 theory, and you consider the original partial differential dynamics, you take your kink, okay, and anti-kink, and I'm sorry, there is a typo. You assume that they are separated at the initial time. So there should be plus x0, let's say, and here minus x0. And this x0, the initial position of kink and anti-kink, should be a large number. And then kink and anti-kink are boosted towards each other. So here is should be minus, I think. And then you do your numerics in your computer and find really a huge variety of possibilities. What can happen is that your kink and anti-kink scatter back to infinity. So here in the first panel, you see this situation. The color is the value of the field. Okay, so kink, it's a tanh x, so it goes from -1 to 1. So it goes from blue to yellow. So this is kink in the initial time. Here is anti-kink, and they come closer. They are boosted towards each other. Come closer. They pass through the vacuum -1, and then they scatter back to infinities. Okay, so this is a sort of one bounce scattering. At another velocity, initial velocity, they can make 2 bounces. For another velocity, they can even make 3 bounces, and they reappear as three particles. But there is a situation when they annihilate to the vacuum. Okay, so there are 2 main channels. One is like back scattering, that kink and anti-kink reappear in the finite state. Another possibility is annihilation. Okay, and if you plot what if you plot, Victoria, if you plot the dynamics depending on the initial velocity of your boosted kink and anti-kink, it looks like that. Okay, so it's here I plot the value of the field at the origin. So if it's blue, means that it's 1 at origin. So it means that you are close to plus 1 vacuum. Okay, so let's consider this velocity 0.2. Okay, so at the beginning, the vacuum was the value field at the origin was 1. So kink and anti-kink, they were far away. Then they come closer. They pass through -1. Okay, through another vacuum. They make okay. Then they try to escape. And the value of the field is almost 1, but they cannot. They pass through another -1 value, and then they eventually they escape. Okay, so this is the 2 bounce window. There is another 2 bounce window, but there are also 3 bounce windows. There are also 4 bounce windows and 5 bounce windows, and yeah, they form a sort of fractal structure. If you magnify, if you zoom, for instance, this regime, then you will see almost the same structure. It will repeat, and then you can zoom again, and you will find again the same structure. So, okay, this is the famous fractal structure observed in the final state formation in kink-antikink collision. And yeah, we have this Bion windows. We have also, N-bounce windows. We have also Bion chimneys where kink and anti-kink form a Bion, a sort of quasi-breather, which oscillates and emits some radiation, and eventually it decays to a vacuum. Okay, so this is the situation in a full field theory. So you would like to understand this dynamics why it's like that. What is the reason for this complicated pattern? And one way to explain it is exactly to construct a collective coordinate model. Okay, because people for many years conjectured that this pattern, this complicated picture, is due to a resonant energy transfer. Okay, you have a kinetic degrees of freedom, which is related to the velocity of kink and is really behind this little a modulus, which measures the position of your kink. And yeah, there is also internal degrees of freedom, which is what we introduced before, which is the shape mode. Okay, so the transfer of energy between these kinetic degrees of freedom and the internal degrees of freedom was conjectured to be like origin of this complicated structure. But then we need an evidence. We need a sort of not a proof, but of course it's not a proof in a strict mathematical sense, but yeah, very good evidence that exactly it's like that. So to show it, we would like to have a collective coordinate model, okay, based on these 2 degrees of freedom, on kinetic 0 mode degrees of freedom and on the shape mode, which is the internal degrees of freedom. Okay, so we do have this, we even consider it a restricted set of configurations, which has these 2 degrees of freedom, right? But it was before, right? Okay, it's here. Okay. But if you use this superposition, then there are some problems, basically mathematical problems, that your moduli space has singularity. And in this case, this singularity is not a physical singularity, but it's sort of singularity, apparent singularity due to not so well assumed coordinates. So you have to improve it, and you have to, instead of this capital A, take capital B, which is the shape mode again, but divided by tanh A. It's because your original superposition produces a null vector problem. Okay. It means that for A equals 0, your metric has determinant of your metric is 0. And it means also that your effective model as a second order differential equation is badly defined at this point. Simply one of the second derivative, it's in this case it's second derivative of B, is multiplied by a function which vanishes at the point where A is equal to 0. Okay, to cure it, you have to change the coordinates, and then you remove the null vector problem. And then also it's important to carefully guess or obtain the initial data for your effective model. Okay, so you take your configurations, which where you cured the the null vector problem, you plug them into your original theory, you obtain the effective Lagrangian, and then you compute the dynamics. But as I said, it's important to properly understood the initial conditions for this dynamics. But if you do this, okay, I will not explain you in more detail because I want to go to other cases. But if you do this and you do your numerics in the collective coordinate model, it's a very simple model. It has only 2 degrees of freedom. Then you get this this plot, this figure on the right hand side. And if you compare with the original results from the full field theory, the agreement is really like spectacular, right? There are some differences, of course, because your model, your collective model, is extremely simple. It has only 2 degrees of freedom, but qualitatively it captures the structure. You see there is a 2 bounce window. Here is this 2 bounce window. There's another 2 bounce. Here it is. There are a sequence of 2 bounce windows, and they are reproduced in the effective model. There are 3 and more bounce windows, and this, the agreement is quite good. Of course, it cannot be like exact agreement, perfect agreement, because, for instance, here there's basically all byons, okay, all these byon chimneys, they eventually dissolve into free kink and anti-kink, because there is no other channel of the energy transmission. Here, byons decay into the vacuum due to the emission of radiation. In the effective model, we do not have radiation. Okay, so these byons cannot decay to the vacuum. They eventually will emit the solitons. But it's, this is the limitation which we are aware from people are aware from the very beginning. Okay, but this result is really very nice, and it shows that such a frozen vibrational moduli space, okay, the most simple superposition of free soliton moduli spaces works really almost one can say unexpectedly well. Okay. Okay. So I have still like 15 minutes or 13 minutes. Let's go to the case where such a frozen vibrational moduli space construction is not sufficient, it's not enough. And the fact that your modes excited on kinks, on solitons, change is very important, okay? So, as I said, modes, internal modes hosted by a soliton, they can change during the interaction, during a collision, okay? So, for instance, one possibility is that a massive mode, a normal mode with given mass or omega, can enter the continuum spectrum, okay? So it means that such a mode, such a linear normal mode is not a normal mode any longer. It becomes a quasi-normal mode. Okay? So it decays. It's linear. In a linear perturbation, it means that this mode would decay. It wouldn't oscillate forever. So for instance, from the usual in the usual construction of the collective coordinate model, this quasi-normal state, quasi-normal mode is not included usually, right? So it means that your set of restricted configurations drastically changes, okay, when your mode enters the continuum spectrum. And in fact, this transition is very important if your process is a process on top of BPS sector. Okay, so if you have a solitons in a BPS solitons, which means that solitons do not interact statically, okay, then this fact that a mode enters the continuum plays a crucial role. So the simplest field theory, when you can observe this situation, because the very interesting application of this idea is, for instance, for abelian Higgs vortices at the critical coupling, but this is a complicated setup. The simplest setup is sort of modification of phi to 4 theory, okay, with an impurity. So here is a Lagrangian describing a kink theory, a phi to 4 theory, with an impurity which is coupled in what we call a BPS manner. Okay, it's called BPS manner because you can find out that single kink, okay, is a solution of this first order linear equation, and because it's a first order linear differential equation, your solutions are parametrized by a constant. Okay? So it means that although you have an impurity, your kink can be placed at any distance from this impurity, and all these configurations have exactly the same energy. So this is the case with the impurity with the parameter alpha equals -1, here is +1, where alpha is this parameter, okay? But it's not essential. But the point is that you can find solutions, your kink, here anti-kink, okay, it goes from 1 to -1. So this anti-kink can be put at any distance from the soliton. Perhaps the right panel is easier to see. Here you have anti-kink, okay, here, and your impurity is at the origin. Okay, so here is the anti-kink is before impurity, and the yellow is the anti-kink which is beyond the impurity. Okay, but it can be placed at any position, and all these configurations have exactly the same energy. So you do have access to the canonical moduli space. You can build up your canonical moduli space because kink impurity state is a BPS state. Okay. All right. So yeah, you can consider the simplest dynamics and compute your effective model, which is one-dimensional with one-dimensional moduli space, and it's exactly the dynamics is just that the kink passes through impurity. Now the velocity is not constant, but yeah, everything is described by the usual moduli space dynamics, one-dimensional. But what is important is that although the energy is constant with when you change the distance between the soliton and the impurity, the structure of the modes is not constant. It varies. Okay, if your impurity is strong enough, if this alpha is, for instance, 3, but it means that your impurity is strong. You see, at the beginning, when kink is far away from the impurity, x0 is this parameter which measures the distance between the soliton and impurity. If this distance is big, your kink is just a pure phi to the 4 theory kink or anti-kink, and it has exactly one mode, shape mode, with the right frequency omega squared equals 3. Okay, but once the kink or anti-kink here approaches the impurity, okay, the mode becomes deformed. Okay? Its frequency changes, and at some point it enters the mass threshold, and here the continuous spectrum begins. Okay, so yeah, so to what we can do now, we can consider the dynamical vibrational moduli space, which means that we do almost the same as we did for the phi to 4 theory, but now we can do something a little bit better because we can compute the form of the mode at any distance between the soliton and the impurity. This little a is exactly x0. This is the same number. Okay, so we have a mode, okay, which frequency changes, which its form, functional form, also changes when we approach the impurity. And now we plug this expression. Okay, you see the difference. Before, this shape mode was all the time the same. This eta function was just x minus a, okay, where eta was just a usual shape mode of the kink or anti-kink. Here we know that the shape mode changes. Okay, so if we plug at any a, at any or any x0, we can compute this mode numerically, find how it looks, and then yeah, plug it here, and then plug it into the Lagrangian and construct the effective theory, effective collective coordinate model. Okay, and you see that of course you have two-dimensional moduli space. It has non-trivial metric which multiplies the dynamics of little a, and there is also a term like potential, effective potential. And the crucial observation is that this metric GAA has 3 components, and these components diverge at the point where your mode enters the continuum. Okay, basically it means when you compute the mode, you have to all these modes, okay, are normalized, of course. But when you normalize this mode, this at the moment when the mode enters the continuum, this is really produces infinities at other places. This is what you can say. Basically, this mode once you approach the point where the mode enters the continuum, the mode spreads more and more. And of course, you can normalize all the time this mode, but it means that at another point of your effective Lagrangian, this normalization will produce some bigger and bigger and bigger numbers, and eventually it will produce infinities. Okay, so the metric, the effective metric on the moduli space diverges, what we computed numerically. Okay, so yeah, it means that your moduli space does have a singularity, and it's not singularity because of some badly assumed coordinate system, but it looks physically, right? It's the mathematical reason for this singularity is the fact that your mode is not a normal mode any longer, but is the quasi-normal mode, for instance. Okay, so we observe a collapse of the moduli space, and the question is whether there is a physical effect behind this, and there is. If you have your kink, and I think I will stop at this point. If you have your kink, antikink here, okay? Here what I plot is the position of the incoming antikink, which is boosted in the full theory towards the impurity located at origin, okay? If the kink, if the antikink is boosted, just boosted, and no initial, and we do not excite any mode, we do not excite this shape mode at the beginning, then the dynamics is exactly like dynamics covered by the moduli space, one-dimensional moduli space. So the antikink passes through the impurity. Okay, it's all the time you go through energetically equivalent solutions. But once you excite the mode, the shape mode, then they can, funny thing can happen. And let's focus on the right panel. If the amplitude of the mode is has a kind of this initially excited amplitude of your mode has a sort of critical value, then your soliton will form a long-living state. Okay, it's like stationary state. So the soliton will almost stay at this dashed line, okay, and cannot pass it, cannot go back. Okay, so tuning this this amplitude, your soliton can really form infinitely long staying state. Okay, if your amplitude is bigger than this critical value, then your soliton will be reflected at this point, at this dashed line. If your amplitude is smaller, it will pass through this dashed line. And what is this dashed line point? Okay, this dashed line point, line, is exactly line corresponding to the distance between the soliton and the impurity at which your mode you excite goes to the continuous spectrum. So this is exactly the point where the moduli space has this singularity. Okay, so yes, soliton feels the singularity of your moduli space. You can say in this word. So the singularity of the moduli space is reflected by the physical effect that the soliton sees a sort of barrier in the dynamics, and if the mode is excited sufficiently, then soliton is reflected. If it's excited less, the soliton passes, and if it's excited in this critical amount, then it forms a stationary state. Okay, and this phenomenon is very selective. Okay, because if you, for instance, have another mode in your system, okay, and this mode has also a point where it goes to the continuum spectrum, then excitation of one mode, I mean, if you excite the one mode, then you will never see the singularity on the moduli space related to the other mode. Okay, so this phenomenon is very selective. We call it spectral wall because it's a wall felt by soliton occurring in the dynamics, but it's due to the drastical change of the spectral structure. Okay, so yeah, I think it's a good time to stop. Okay, I will not go further. I underestimated or overestimated my ability to talk. But to summarize, okay, just in 1 minute. So I wanted to convince you that the collective coordinate method is really a powerful tool. It describes not only the very simple dynamics like just boosted kink or kink which vibrates. No, it describes very complicated, chaotic dynamics of kink-antikink collision in non-integrable field theories. Okay? But sometimes, okay, this usual approach, which is the frozen vibrational moduli space construction, where you build your moduli space, your collective coordinate model, from using just free particle blocks, let's say, it's not enough. You have to really take into account the fact that the spectral structure, the mode structure, differs whether the solitons are far away from each other or they are close to each other. And once you do it, then you can discover and understand some phenomena which are like true phenomena, which sometimes can be crucial for the dynamics of topological solitons. And yeah, I leave you with two problems which I mentioned during the talk. One is this observation that you start with Lorentz or relativistic theory, Lorentz invariant theory, but your collective model is always, almost by construction, it's always a non-relativistic model. This is one problem. Another problem is that once your theory doesn't have any, once your kink or solitons don't have any internal modes, then it's quite problematic to construct more complicated moduli space. Okay, there are two limitations or two problems which need to be really cured. And okay, thank you very much. I think I'm not too over my time. Thank you.
Thank you. Thank you. So thanks for the nice presentation. And if anyone have any question?
Hi, I have a question.
Okay.
Yes.
Hi, Andrzej. Thank you for the presentation. It was very interesting. My question is, have you tried to use a dynamical vibrational moduli space for the 5-4 kink-antikink collisions, and if it would give similar results to what you found with the frozen one?
Yeah, so my answer is no, we didn't try, because our original motivation was really that we expected from the very beginning that you have to use this dynamical vibrational moduli space. That's what we thought from the very beginning. But then what we proved was that you don't have to worry about this, and the simple naive frozen vibrational moduli space works very well. Okay, so yeah, we just somehow we were also surprised, and the deeper answer is that at the moment, for instance, we do not completely understand in which situations the frozen construction is enough, and in which cases the dynamical construction is better. Okay, this is it's not completely clear. One I mean, if your dynamics happens over BPS solutions, right, then we expect that the frozen vibrational moduli space is not correct. It's too simply. But if you consider a dynamics which is far away from being BPS, like kink-antikink annihilation in 5-4 theory, then at the moment where kink and antikink collide, when they collide, the dynamics, in a sense, is very fast. Everything happens very quickly, which means that the kink and antikink somehow don't have time to realize that the mode structure changes. Okay, so that's the reason it's a hand-waving explanation why the frozen vibrational moduli space really works in this case, but we do not have deeper, better understanding.
I see. So you didn't, in this case, you didn't need to use dynamical because the frozen one worked well already.
Yes, exactly. So this is like that, and one way of our current investigations is to really understand the cases where the frozen vibrational moduli space is not enough, and why. What is mathematical reason which tells you that this is too simple.
Okay, I see. It seems like a complicated question to know when it's
no, I mean, this is a very good question, but it's it has to be discovered, the answer.
Okay.
Thank you. Actually, it was my question too. It was funny. So I'm just curious here. If you use the dynamical one, in principle, it can be neutral, or it can get better. This is what we expect, right? I mean, you're taking the simulation result, you're doing the collision that is closer to the thing that is happening. So I wouldn't expect it gets worse. But did you observe to get worse or to stay the same?
No, Azadeh, we didn't try do the dynamical vibrational construction for 5-4. The reason is that then you have to compute numerically
exactly
the mode.
In the whole process, you should do
the whole process. Yes, but the problem is that if you start with a BPS sector, then you can compute in the very well defined manner the mode structure at each point, because at any time you have a static solution.
Yes.
At any distance, right? And in 5-4 model, where you have kink and anti-kink, you have static solutions only in two moments, where kink and anti-kink are infinitely separated, and when they are on top of each other, so you have -1 vacuum. But you do not have static solutions in the middle, I mean interpolating. You have only dynamical solutions, not static. If you consider static configuration and you perturb it, like kink and anti-kink at finite distance, then you will have also negative unstable mode.
Oh.
Right? And then you have to somehow, perhaps take this unstable mode into account. And I don't really know how to cope with this problem at the moment. So you see, if you start with BPS theory, you don't have the negative unstable modes.
Okay. Yeah,
so
that's
in
curious.
5 to 4, but
there are stuff to discover here, right? I mean,
but it would be interesting to, I mean, in the simplest case, you can just forget about this unstable mode. Okay, you can compute what happens with your normal modes and use them in your
like looking at it as snapshots in time, like taking the
yes
solution that you have and then seeing that how the process works.
I don't we haven't done it, and it's because you see that there is this little disagreement for smaller velocities, right? If you compare it so there are like many places where this plot, this dynamics, this moduli space dynamics can be improved. That's true, yes.
Okay, interesting. Thank you.
But I think just as answering your question, I think a situation, a model where this vibrational moduli space, dynamical vibrational moduli space construction can be really applied is vortex dynamics in the abelian Higgs model at the critical coupling, because then you start with the BPS static solutions. And then the transition of the modes should be important. Okay, so this is the setup we would like to also. I mean, I think it's interesting.
So have you found spectral walls on vortices?
No. I mean, I'm saying that this is something I would like to do. Right? I haven't done yet. But it's like physical. Important question whether there are spectral walls in this situation.
Yeah, it seems interesting.
Thank you. Just let's see if there are other questions. I think Fabiano is here too. Saying excellent seminar. Hi.
Hi. Thank you for the seminar, Professor.
Hi,
Professor Atade.
Hi.
Always an honor to listen to you.
Thank you.
I have another question about this figure.
Yes.
Have you tried to simulate the radiation with the damping in the equations or something similar? You think that could work?
Yeah, this is what should be done. One has to do this. Yes, exactly. There are two ways to include radiation. One is just to add a damping, sort of damping factor, damping term to the effective model. Another one is to include at least some of the radiation modes from the original spectrum of the free solitons. Okay. Yes, we want to do this, but the problem is that this damping term, for instance, it seems to be very, very easy to add, of course, but it would be perfect to have, to derive this term from the original theory.
Okay. not just a random damping.
Not just add by hand, right? Because yeah.
I see.
So that's a nice like research project. How exactly to derive a damping term and then plug it here, and then then this fake bion chimneys which are in the moduli space dynamics, they should be true. They should be true bions. They should decay by emission of radiation. Yes.
Okay. Thank you.
But
that's actually an interesting subject to work on, I think.
Yeah, but you see, radiation, this is very closely related to the problem of this non-relativistic form of the effective Lagrangian. Radiation is purely relativistic effect, right? Because the radiation waves travel with the speed of light. And the collective coordinate model is non-relativistic model by the construction. So you see, the problem of the radiation is a bit, it's a bit more complicated, but it's really very, very important. It somehow, touches the basement of this construction. So,
okay. Interesting. Okay, more questions? Okay, if there is no other question.
okay, I can stop sharing.
And close the session, but I mean, you're free to go. Maybe we can take out of the...
Yeah, I will stop recording.
Yes, exactly.
Thanks.